Hello and welcome. Thank you for joining us for the Consulting Specifying Engineer webcast, Power for Industrial Facilities. I'm your host and moderator, Amara Razgas with Consulting Specifying Engineer and CFE Media and Technology. I'll be with you for this hour-long education session. All right, so if you're having trouble with your slides or with the audio, refresh your browser or refresh media. There's a separate button that says refresh media, and you can control the volume settings on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do a couple of system checks before reaching out to an online technician. If you do need help from a technician, type a question into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources on the left side of your screen. Type questions for the presenters in the Ask a Question box on the left side of your screen. You can ask questions at any time, and we'll start the Q&A session in about 45 minutes. If you're interested in receiving one AIA CES approved learning unit, you do need to pass a 10-question exam. To take that learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend that you open it right now because that link will break when this webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. All right, so here are the learning objectives, and we're going to go through this in today's presentation. And please note that any blue underlined text that you see is a hyperlink in that PDF where you can get more information. All right, well, we have lined up two presenters with lots and lots of experience. Zia Salami is a subject matter expert in electrical power systems at CDM Smith, based in North Carolina. Zia has industry and academic experience in electrical power systems and has served in several roles as an advisory engineer, consultant, and academic professor. Zia is a regular contributor and speaker with Consulting Specifying Engineer. Nicole Kosman has more than 15 years of experience in the power industry, and she specializes in power engineering for industrial facilities, environmental retrofit projects, and new fossil fuel plants. She's an electrical engineer at Smith Seckman Reed, where she assists clients by providing technical direction and management on projects from concept to final design. All right, well, I am eager to get started on this topic, but first we're going to ask you to take a quick poll. So the question is, what is your role in electrical and power systems? And if you could please answer that question, you only get one choice here. So if you could let us know a little bit about yourself, we would greatly appreciate it. That'll help us understand better who we're speaking to and have a feel for what we should focus on during this presentation. So thank you very much. The answers are coming in, and thus far, let's see, the majority of respondents are electrical engineers. Okay, so we've got folks with a good basis information already on hand about electrical engineering. Second, we have engineers, not electrical engineers, but engineers with other discipline backgrounds and information. So thank you so much for taking that poll, and let's get started, Nicole.
Thank you, Amara. As Amara said, my background is mostly in fossil fuel power plants, whether they be coal, gas, reciprocating engines, and their respective environmental retrofits, so mostly industrial settings. So today we're going to be talking about typical power supplies to a facility, what the UPS is, its performance characteristics, typical applications, codes and standards, and case studies in modeling and analysis. To start off here, the UPS is an important part of the electrical infrastructure in a facility. I like to call it the unsung hero because if it's doing its job, you will not know it is there. It's just going to hum away. And here is a basic diagram showing the various potential sources of power generation to a facility and how the UPS interconnects with them. So you may be asking yourself, okay, if I have all of these potential forms of generation and a backup generator, why do I need a UPS? Well, UPS, first of all, stands for uninterruptible power supply. There is no startup time for UPS to come online. Upon loss of loss of power, most generation facilities require time to come up to normal speed and voltage. And that time can be anywhere from 5 minutes to several hours or even days. So upon loss of normal power or power fluctuation, the UPS is instantaneously available with a regulated AC output. Therefore, it meets the definition of a reliable AC supply as defined by NEC. The availability of its output approaches that of a DC supply. The UPS consists of several pieces of equipment centered around an inverter. And I'm not going to go into many details about how the inverter works, but I'll describe it briefly because I think it's really cool. It's a solid state device and it mimics an AC current and voltage utilizing a DC power source. So it uses insulator gate bipolar transistors, IGBTs, acting as static on-off switches to reverse the connections between a set of input and output waveforms. Reversing this polarity reverses the flow of current, mimicking the square waveform with positive and negative amplitudes, which creates a very simple sine waveform. So each pulse segment has an average magnitude of current that increases and decreases in correlation with an AC sine waveform. The output voltage is determined by how long those switches are closed, and the frequency of the output is determined by the timing of the pulses. This is typical for a pulse width modulated inverter. There are also ferroresonant inverters, but they are pretty much obsolete. And I think the last time I tried to specify one, I could only find one vendor that still made them. Inverters also use filter techniques and controls to meet time, current, and voltage characteristics that you set for their output, regulating frequency, voltage, and wave shape. There are also other accessories that can be purchased with a UPS system, including a rectifier to convert your AC input to DC that would then go through your inverter, a bypass switch, which will bypass the inverter to an alternate AC supply in case you need to do maintenance on your inverter, a static switch, which transfers the UPS from the inverter to a reserve supply in case of total inverter failure. You can also have an isolation transformer on your AC input for output regulation when the bypass is initiated. It can also be purchased with batteries, including battery chargers, monitoring, and a DC distribution bus. And then finally, an AC panel board can be purchased with the full UPS package. So you can purchase these items separately. For example, you may want to use a facility's battery and distribution bus to supply the DC input to your new UPS. But generally, it's recommended to buy them all as a package so that the UPS's battery is specifically sized to the exact equipment it's feeding. Usually that results in a smaller footprint and a lower cost of the unit. So, when you're specifying a UPS, the most important question to ask is what equipment will it be supplying? In general, typical systems include data centers. You could have a medical UPS feeding medical equipment, computers, communication systems, military facilities, instrumentation controls, and in some cases, even security systems. So while you're thinking about what you're going to be supplying, make sure to confirm the requirements of that equipment, what type of AC supply and restrictions it may have. You need to specify the required runtime at full load. This is generally based on owner's requirements, but also for industrial facilities, that runtime needs to be sufficient for any processes that are required to shut down equipment safely. Specify the battery type, your system configuration, including required redundancy of inputs, and also external connectivity requirements. For example, if you are subject to the requirement for a disconnecting means to be provided for IT equipment and associated HVAC systems per NEC 64510, you can utilize shunt shift breakers in your AC panel and connect them to an emergency power off switch near the entrance of the room. So there are three general configurations of a UPS. The first one that we'll go through is an offline or standby UPS. It is the most basic and less expensive with a high efficiency and still a small transfer time. These type of UPSs are best suited for smaller loads under 1500 VA. They're not typically recommended for critical loads or sensitive equipment. They provide surge protection and a battery backup. So it protects you against power problems like spikes, transients, and electrical noise, and they're most suited for items like home computers, printers, scanners, that type of thing. The next one to go through is the online or double conversion UPS. This is the most reliable type of UPS, therefore the most expensive. It's called double conversion because it includes a rectifier. So you're converting your AC input to DC and then DC back to AC. Doing that means that the output is independent of any voltage or frequency abnormalities that may be occurring on the input to the UPS. Batteries are always connected through the inverter in this type of UPS, so there is zero transfer time. This makes it ideal for critical equipment or equipment that requires electrical isolation. So this UPS is going to protect you against any sags, burnouts, surges, spikes, transients, electrical noise, harmonics, frequency variation, and main power failure. The most basic configuration is shown here, but you can also purchase them with 2 AC inputs and redundant battery chargers. The third type of UPS is called line interactive. This is kind of a step above the offline type of UPS in that it's going to protect you against voltage issues. It's voltage independent. It's also called a VI UPS system. It has a voltage stabilizer or isolation transformer that enables the output to remain within your predetermined voltage window. It does have a small transfer time. It's really suitable for smaller, less critical applications such as PCs, telephone systems, non-critical networking equipment, and small motor loads. So it will not protect you against those harmonics and frequency variations, but you still will be protected against sags, burnouts, surges, spikes, transients, electrical noise, and main power failure. So regardless of configuration, an effective UPS design for a facility includes these following features: high levels of reliability and efficiency, minimal transition times between normal backup operations, input current with reduced harmonic distortion, regulated output voltage with low harmonic distortion, unaffected by input voltage or load changes, a low degree of electromagnetic interference and acoustic noise, relatively low cost, weight, and size requirements. The reliability and performance of the UPS is only as good as its battery types. There are 3 main types that I want to touch on that you will need to decide which to specify. Those are valve-regulated lead acid, flooded cell lead acid, and lithium-ion. Things to consider about each one of these are the upfront cost, long-term cost, physical size, containment requirements, code implications, and lifespan. VLA or vented lead acid have about 20 years of a lifespan, so a relatively long life. They're very reliable and they have high amp hour ratings. However, they do require quarterly maintenance. They're generally more expensive than valve regulated lead acid. They're very heavy. Usually they require a special racking mechanism to be replaced and lift them out of their rack. They have a large footprint and they contain large quantities of acid electrolyte, which means you need some sort of battery containment in most cases and ventilation. The valve regulated have a smaller lifespan of 5 years. They are the lowest cost of all three and lowest maintenance. They still have a ventilation requirement because they do emit hydrogen into the atmosphere, but it's at a much smaller rate than VLA. And they have a very short life is the con there. Lithium-ion are gaining more popularity, I would say, because they have less cost over the life of their battery. The lifespan is about 10 to 12 years. They're much lighter and smaller even than VRLA, less maintenance. They can operate at higher temperatures, faster recharge time, but they're much more expensive. This could be changing, but they're about 100% more than VRLA. And there's some restrictions on shipping methods. There's higher risk of thermal runaway. So regardless of type, the temperature of your battery room is important. For every 15 degree Fahrenheit average annual temperature above 77 degree Fahrenheit, life of the battery is reduced by 50%. So it's really important to coordinate your battery shipping with the manufacturer and your storing with the owner. So when you're specifying your battery type, be cognizant of space requirements, battery containment requirements, smoke detection, ventilation, temperature requirements, and the room rating per IBC Table 509 and the International Fire Code Table 1206.2. So for example, with lead acid batteries, they have that hydrogen expulsion. So they more than likely will need ventilation. Make sure to have your vent fans on backup power because you definitely don't want those going out of service. You may also need an eye wash or shower. VRLA, although they still have the hydrogen expulsion, depending on the size, you may or may not need ventilation for them. Lithium-ion have a lot more requirements. If they are over 20 kilowatt hours, they cannot be located in rooms where the floor is more than 75 feet above the fire department vehicle access or more than 30 feet below the finished floor of the lowest level of exit discharge. Each battery array, limited to 50 kilowatt hours each, needs to be spaced a minimum of 3 feet from other arrays and from walls in the storage room or area, unless closer spacing is allowed by the authority having jurisdiction based on performance in UL 9540A testing. Systems exceeding 600 kilowatt hours require H2 occupancy classification. The room requires sprinklers with a minimum flow of 3 gallons per square meter per minute or other suppression system, and they require smoke detection. Advanced early warning detection in the form of aspiration-type gas sensing detectors should be included for large energy storage applications to detect potential thermal runaway before significant damage occurs. But this is usually an application that's only required for battery storage type projects. Here are some of the typical major codes and standards for UPS systems. Take a look there. I'm not going to read them off for you. And I will let Zia take it away from there.
Thanks, Nicole. Now let's focus on UPS connection and its behavior when we're performing power system study in a facility. by having this internal connection, as you see, the UPS has, as Nicole mentioned, input and output. Input, the charger converting the AC to DC, then the inverter converting DC to AC output. In this connection, that's a typical UPS system that has a box and connected to a battery system, as Nicole pointed out, including the bypass. In case of any problem with the UPS system, or during the maintenance, we will use bypass to perform the connectivity between the injecting the power to the load. Now, before we continue our discussion, mainly I'm focusing on the system analysis when there is a UPS in a facility. I want to point out a short video clip that I pay attention to this one. As I discussed in my previous slide, UPS has the AC input, AC output terminal, and also DC terminal. Typical rating for the UPS is based on the kVA. For example, in this case, 200 kVA with efficiency of 96% and power factor of 98%, which is based on the vendor information. The voltage rating of the input and output of the UPS can be variation between 10 to 15% based on the vendor specific, and of course can be designed based on different voltage level as requested. The output of the UPS can be 3-phase or single phase based on the connection and the design, and the input is typically 3-phase system. The DC connection, the DC terminal can be connected to a battery or in different format that I will discuss. Can be, for example, rated 480, 250, and so. The other characteristic that important for the UPS is a bypass system in case the UPS has a repair, maintenance, or malfunctioning, that the power can be from the bypass that can be designed. In some electrical software package such as ETAP, this bypass switch can be modeled within the build, within the UPS component, and can be analyzed within the component. The other characteristic that is important for the UPS, the short circuit contribution to the AC and DC system. This is typically limited by vendor characteristic and specific vendor limit percentage, typically 150% to AC output of the terminal, or to the DC terminal based on the FLA of the AC, rated AC or DC system. We will see this case in our case study in the next few slides. Other important characteristic that we definitely need to consider, UPS is source of harmonic for both voltage and current distortion, and can be analyzed, should be analyzed actually, based on the type of the model that we may have, either the 6 pulse, 12 pulse, 18, or different type of injection, current injection or voltage injection for the harmonic distortion analysis. Now let's go back to our presentation, and we will continue from our presentation. I will discuss several of these doc parameters that we discuss in the video clip in later slides. Now, the second possible UPS connection that I want to point it out, this is mainly when we have a larger facility and we have additional DC loads. We can have parallel the the charger in addition to the UPS system to perform redundant charging the battery at the same time, either from the UPS and from the charger, and the same time we have a DC load connected. Therefore, there are several possible connection, depend on the facility, depend on application, but I just want to point it out, that application that can supply to the AC critical load and also the DC load in the same time, and the battery can be charged either through the UPS or from the charger and supply the charging and discharging. And if in case of the abnormal condition, the battery can kick in and provide the power to the system. Now, I would like to focus in here on utilizing electrical power system, and when we have a UPS to perform several studies such as the load flow, short circuit, arc flash, and harmonic. UPS, as pointed out in the video clip, has a certain characteristic that we should keep in mind when we perform such a study, including the modeling and analysis. Here, a typical facility which feeding from the 2 feeder 13.8 to the facility, and then we do have 4 kV system, and then 480 volt low voltage which fed from the UPS system. UPS is connected to AC, is connected to backup generator. As Nicole pointed out, that facility can have the first line of source of input to the facility in general would be from the utility, and then would be from the backup generator, and possibility renewable, which in parallel, and also the UPS. Therefore, the focus here would be on the UPS system. Our critical load connected to this bus by 200 kVA critical load. I pointed out in the video clip that what is this number typically means. That means that the load that is supposed to be supported by the UPS system. Now, let's look at this here. The load required 200 kVA, and we're supplying 200 kVA through the, let's call it normal operation. Normal operation in this case means that the power going through the UPS, the inverter, and supplying the load. And in the same time, we are charging the battery. That's something that keep in mind, that when there is a sizing involved, we need to consider that not only the amount of the load that we need to supply, we also need to pay attention to the amount of the required power needs to charge the battery in the same time. This is actually the one of the type of the UPS that Nicole pointed out, online or double convention UPS system. Now, if you look at it here, the voltage on the secondary or the output is controlled and is 100%. Therefore, that load flow that provides you not only the amount of the power that you need to size the UPS, it also provides you what the feeder and circuit breaker should be sized based on the worst case possibility, the amount of the power, the current, and going through the system, including the voltage at the output. Now, let's look at the other case. In this case, now the backup generator can supply power to the facility in case the utility is disconnected, or typically, again, may not be the case, but in general, we have a backup or emergency generator that supply to the system. Here, the same as you already seen it before, the same type 200 kVA critical load, and doesn't matter if it's coming from the utility, coming from the gen, there's still you need to provide 200 kVA, and as you see here, the same amount, but this what we call it another configuration, which now fed from the gen. Now, let's look at the next configuration, which I really want to emphasize on that bypass. Because sometimes worst case scenario, either in this case, load flow, and later on you will see on the short circuit, you will see the bypass, if that's possible. Some UPS system may not have a bypass, or which most likely not the case, but let's assume they say, okay, we're never going to use the bypass. That's a different story. But if you have a bypass and there is a possibility, which most likely you have, then should be analyzed. Now, the same amount, 200 kVA load or power feeding to the critical load. But if you pay attention here, the voltage is much lower, around 94%. Therefore, the load flow provides you the characteristic of the system, the voltage frequency in different configuration. Now let's look at the next configuration. Now I'm losing the outside power, I'm losing the gen, and there is no input from the AC source. Now that's the time that the UPS will kick in, as been pointed out in this presentation by Nicole, and we'll continue to discuss on that. Now the UPS is kick in on the battery DC system and supply the amount of required that we already had, the same 200 kVA from the battery. And then we able to look at the sizing for the DC system in case that is a larger facility and your connection have the battery has a circuit breaker, the bus, and the cable. Therefore, you can able to sizing the DC system. Now, just some notable consideration I want to point out here that always we need to analyze all possible scenario when dealing with the UPS system. Again, in this presentation, we are focusing mainly on the UPS, considering the battery charging when we are able to, or when we're designing sizing the UPS and considering the battery charging that most of the people sometimes will not consider that. Main standard related to load flow, I just want to point it out for information, is IEEE 3002.2. Now let's look at the other study that is important for not sizing the circuit breaker, sizing the bus switchgear, and withstand capability of the equipment is a short circuit. One of the characteristics, as pointed out in the video clip, that if assuming this is a normal operation now, again, normal operation means that the power, as I pointed out, coming through the charger, the inverter, the UPS system, and the UPS will control the output of the AC contribution to the output by the amount of what designed by the manufacturer. In this case, for example, this manufacturer designed that the limit the current output or the fault current to 150% of the rated output full load amps, which happen to be in this case 400 amps. And as you see here, the output of the inverter only injecting 400 amps to this panel, or the panel that is combined, the critical load is located here. And other characteristic that UPS has feeding back to the system is 0 amps. That is something that we need to consider, and which actually is an advantage for us, considering, for example, comparing with the induction motor has contribution, short circuit contribution here is about 400, but the UPS, as you see here, feedback the short circuit contribution back to the system is 0, and then the current, the short circuit in this right here around 1.3 kA, and so. Now let's look at different configuration. This is a bypass configuration. As you see here now, the fault or the amount of the fault at the output of the UPS connected, that again, that the same spot is almost 7-8 times, because now we don't have the UPS to control the output or the fault, and all the fault coming from the system, as you see here, about 7,000 amps flowing into bypass and injecting to that one. Therefore, we need to have, as I mentioned again, looking into all configuration when we're analyzing, because sometimes, maybe most of the time, bypass would be the worst case condition, and the system should be designed based on that, as you see here. Now, the next configuration that I want to show you, now let's look at the DC system. The same contribution from the UPS to DC system has a limitation or multiplication based on the percent of the DC rated. In this case, the UPS only controlling around 640 amps to the DC system, therefore as limited and controlling by the the UPS system. Now, summarizing of the notable consideration, again, possible all the time, looking into different configuration. Short circuit to the AC would be multiplication of the factor of the percent full load amps. The same for DC, as I pointed out. DC in the larger facility, when they have a separate or also extended DC system, DC short circuit and the withstand capability should be evaluated. Major standard related to short circuit, just for information, if you want to check it out, is 3002.3. The next study that I want to point it out, concerned with the UPS, would be arc flash study. Again, I'm focusing on this area right now. Normal operation, the power coming from the current coming from the UPS system, and if we are analyzing the output of the UPS, one thing that we need to consider, that we always need to do both input and output arc flash assessment, because they would be a different incident energy calculation, and definitely there would be different label that you may have to use. Focusing on here on the output is about 0.16 calorie per centimeter square. And this is the time that we have the UPS normal operation. On the next, we're going to look at into bypass. Now, as you see here, the incident energy almost several times. Still 0.7 is low, but again, this is a case study. In the reality, you may have instant energy larger than you wanted to have. Therefore, analyzing that will provide you provide you a different number. And so now, one thing, again, going back to the DC system, some people will ignore to analyze DC system arc flash, and because we always do the maintenance on the battery, breaker, cable on the DC system. Therefore, we definitely want to have a assessment on that, the DC assessment, DC arc flash assessment on the DC system, to provide, again, the instant energy, and finally the label that we can install on the equipment. Some notable consideration, again, that we should evaluate both input and output, evaluate the bypass and provide the worst case configuration. The DC system should be evaluated, and two major code and standard related to arc flash is the 1584 2018 latest. Of course, again, pointed out that this IEEE will not cover the DC system. They pointed out a few references in here, and also NFPA 70E standard for electrical safety in the workplace. The last study, at least for this presentation, I want to point out on the harmonic study, because having the UPS equipment or component such as UPS or VFD will source of the harmonic, and we definitely need to monitor that and analyze that, and provide make sure that we don't have the power quality issue. Now, in this case, in this scenario, I started with the bypass because I want to point out a few things. Let's assume the entire system here, only the UPS here has a source of harmonic distortion, voltage and current, to make the presentation. If you see here, the total harmonic distortion from the input and output is 0, because we don't have any harmonic distortion or the source of harmonic. And as you see here, nice waveform, and no individual harmonic exists in this system. Again, just want to point it out. I have a VFD, but I assume there is no source of harmonic for that. But in reality, VFD has the source of harmonic, but I just, for simplicity, I ignore that. Now let's add the normal operation, bring the UPS. You saw on the video clip on that you can select, or based on the manufacturer, they might be 6 pulse, 12 pulse, 18 pulse, type of rectifier which producing the harmonic distortion. And now look at the input and output total harmonic distortion. Now I'm jumping to 7%, and here almost to 12%, which we know that limit in this case, we should not go above 8% at the bus and 5% the individual. Now let's look at the waveform, and obviously this is not the nice waveform that we saw before. And here, if I'm looking at the individual, this is the 11th third individual harmonic, is about 9 and 7, which the limit is about 5%, and that is something needs to be done. Here, just a summary of that one. UPS is source of the current and voltage harmonic. Harmonic should be evaluated, should be controlled and mitigate, because power quality issue is a hidden problem that sometimes you may not notice and create a lot of problem. Again, the topic here is not harmonic, but just I just want to point it out. The major standard related to harmonic is IEEE 591. That would be something that you can refer to. Well, that's all I have for That's what all I have for presentation time here. And thanks for participation. I hope that helped a bit. Now I pass it to Amara for the rest of the presentation. Thank you.
Excellent. Well, thank you so much, Zia, and thank you, Nicole. That is a lot of information. As a reminder, you can earn one AIA CES approved learning unit for this event, and you do need to pass a 10-question exam. To take that learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. And it does open in a new window, so I suggest you open that window right now. The whole thing will shut down when the webcast ends. However, if you have that browser window open, you will still have access to it. All right, and if you'd like to earn additional learning units or online continuing education, you can visit CFE.edu. There's a course on how to engineer for future-ready healthcare buildings, for example, and Virtual Training Week is right around the corner this fall. Please check it out. All right, so let's take some questions. Type your question into the Ask a Question box, and please type the presenter's name before the question so I know who should answer it. We will get to as many questions as time allows. Questions that we don't get to verbally today will be posted online with the archived version of this webcast. You can go to www.csemag.com to access that Q&A. And don't forget to download the presentation slides. You can use the Event Resources tab on the left side of your screen. Alrighty here. So Nicole, I'm going to send this first question to you. Should UPSs for critical systems be located in space where they are protected? Do they need to be located in environmentally controlled spaces?
Yes, they do need to be environmentally controlled in order to sustain their lifespan, the batteries especially. And in some cases, you may want to locate the batteries in their own room to cut down on your HVAC costs, so that you have dedicated HVAC for them, because it's really the batteries that are more sensitive to temperature. Now, the other components of the UPS can be susceptible to dust and dirt and that type of thing. So that's why it's like any other piece of electrical equipment, it's important to have them in their own room in a controlled environment, positive pressure to help keep them clean and working correctly.
Great. Thank you, Nicole. Zia, this next question is for you. What are the most common errors when designing a UPS system?
Good question. Most common error to me is sizing UPS based on the initial or existing load and not considering the future demand. Load increasing and demand increasing, and is not being considered if we starting with the initial and existing. That's a typical error that I see. The second, as I pointed out in the presentation, UPS will create harmonic distortion. Therefore, we sometimes ignore, and we need to pay close attention. The third one, probably there are many, but the third one that I can think of, selection of the right battery with your application and the amount of runtime that you need. For example, if you need for the safe shutdown, if you need for the backup your data center, if you need providing different application, you need 10 minutes, 30 minutes, 1 hour. Therefore, sometimes that would not be considered at the beginning of the design and may create error in later time.
All right, thanks, Zia. And I'm going to follow that train of thought, Nicole. This next question is for you about applications. I'm familiar with specifying UPS systems for computer room environments, but what are the differences in UPS systems for industrial applications?
That's a great question. In general, in industrial applications, you want to specify more robust components and more redundancy, which is going to direct you towards that double conversion type 2 UPS. So you may have two AC inputs from separate AC panels, redundant, 100% redundant battery chargers, again fed from separate AC panels, and they usually utilize VLA or VRLA batteries.
Okay, sure. Thank you. Zia, let's talk about sizing here for a moment. What are the major parameters that we need to consider when sizing a UPS system?
As we pointed out in presentation, in general, is depend on the connected load that we need, including the future demand, or 10%, 20%. In addition to considering the same time battery charging in the same time. One other thing that we need to also consider, the overloading of the UPS has a percent overloading. That should be also considered, because when we designing the cable feeder to the UPS and the breaker to the UPS, we definitely need to consider the overloading capability of the UPS. Now 110%, 120%, whatever the number is, that has to be considered for the sizing. And also, as I again mentioned a few times, the batteries sizing becomes really important, because that should be able to supply the load, the demand, including the losses in the system and the runtime. Those at least 4 or 5 parameters should be considered when we sizing the UPS system.
Very good. Thank you. All right, Nicole, this is kind of a clarification, or perhaps a misunderstanding on the part of the attendee. It sounded like you compared valve-regulated lead acid batteries to flooded cell batteries. Like, which ones have longer life? Can you go over that for just a second again?
Sure, let's review that. So VLA lead acid batteries are also known as flooded cell batteries. And I was comparing them to VRLA, which is the valve-regulated lead acid, which are considerably smaller. The flooded cell do have a longer lifespan, but they require more maintenance.
Great, thank you. Zia, let's take this next one here. What are the main environmental conditions that impact a UPS system?
There's at least several that I can think of. The main and most important, the heat, because typically UPS system size, the capability, rated capability is based on specific temperature by the manufacturer. Now, this can be 25C, 30C. either it would be internal for the use of internal or external, but it's defined based on the temperature. Therefore, now any variation outside that temperature definitely will impact on the UPS. Dust, humidity, air quality, all can have impact on the UPS condition, definitely.
All right, thank you. Nicole, we're going to kind of continue the conversation here about batteries. There seem to be a lot of questions. You mentioned lithium-ion batteries. How about lithium iron phosphate batteries? Can you talk a little bit about the difference?
So it's really hard to address all the components of a UPS system because there are so many interesting technologies related to batteries and inverters. It's a lot of content. So I tried to zero in on the 3 most common types of batteries, but you are correct. There are a lot of new and exciting types of batteries coming on the market. It'll be really interesting to see what other new technologies are going to come forth. This market is extremely competitive. I think we'll see a lot of new offerings coming out here with hopefully safer options.
Right, true. All right, Zia, another question for you. Again, we're on the subject of batteries. How do you determine the battery charging kVA for sizing breaker and feeder?
Well, I mean, regarding the charging the battery, depend again on the battery state of the charge. Sometimes the battery can only go, for example, 20%, 30% instead of the charge. If we are having a good design, that would probably I would do that based on the minimum state of the charge. Let's assume the minimum state of the charge is 30%, and we need to charge the battery the remaining, which typically goes to, let's say, 90%. I would definitely count the minimum that the battery can go down. Then we have to charge it up. Therefore, I will utilizing that amount for sizing how much the UPS I need for the UPS sizing. Now, if you are looking for the DC, but I think the question mainly was that on the DC part for the breaker and the cable, I will look at the other side, how much battery injecting and the maximum possibility that battery can injecting. I have a presentation, a slide on the load flow, for example, when the system fed from the the DC system. Therefore, that amount, that the maximum amount that the battery should supply the load, including again always losses, that should be considered for the DC circuit breaker, cable, and other component on the DC sizing.
Sure, thanks, Zia. Nicole, back to you. Are UPS battery banks arranged in multiple parallel strings to allow for failure?
Usually they are not, but what we do a lot of times ask for is that battery monitoring system. So that should give the owner a heads up before battery failure to tell them, something's going on with your batteries here. You need to replace one in your string. But usually you don't specify the system to have redundant batteries.
All right, thank you. Zia, moving back to you. Does the VFD limit the contribution to short circuits the same way the UPS does?
That is correct. VFD also contribute in the output, the same as what you saw in the UPS short circuit to the limit. The limit can be 150%, the same as what we saw. And back to the system is going to be 0, the same as what we saw on the UPS. Therefore, contribution back to the system is 0 amps. Contribution back to or injecting to the AC output would be based on the limit, again, those manufacturer design, typically 150%. that would be the case.
Sure. Okay. Thank you. Nicole, does equipment need pure sine wave power?
No, it does not. And that's what's nice about having these different types of UPSs. If you need to look at what equipment you are feeding, because there is equipment that can be sustained through a small transfer time. So maybe a less costly offline UPS would be better suited to your application.
Okay, sure. Thank you. Let's see here, Zia. This is referring to one of your studies. Does the data used in the study for harmonics from UPS come from the UPS manufacturer, or is it part of the ETAP program? Can you tell us about that, please?
Correct. In general, all the electrical software package such as ETAP, SCAM, Easy Power, and more, they have a library that they, at least as a standard library, which can be used for assuming that there is no data available, those going to be from the library. Therefore, answer to your question, that data that I was select was based on the typical standard, I believe, 6-pulse reactifier from the ETAB library, and not from the actual manufacturer. And speaking of that, it's always good to look into if the manufacturer can provide you the type of the reactifier or the type of source from manufacturer first. And of course, if you not able to provide or receive those information, our backup option always going back to a software typical standard data that we typically use.
Okay, good. Thank you. Nicole, another question for you. Can you please give some info about grounding of equipment?
Sure. Generally, your UPS system is recommended to be ungrounded. But having said that, I have run into instances where different manufacturers have different grounding requirements. So it's important to follow what they recommend because they are monitoring ground fault on their system and they may have different grounding requirements.
Sure. Okay. So Zia, it looks like we have time for one last question. I'm going to send this one over to you. Let's see here. When sizing the UPS, do we need to consider the inrush of the equipment, such as transformer, downstream, or motor?
That's a good question. As far as the inrush, we typically do not consider the inrush for sizing a protected device, circuit breaker, cable, or UPS system. Because typical, like for example, as the question was, the transformer inrush lasts only maybe 6-7 cycle, really a small time. However, we will considering when we do the setting of protected device, we want to make sure we're not tripping or on the inrush. In this case, was question on the transformer, but not for the sizing. But definitely, we need to consider when we're performing protection and coordination study and to count for those fast several cycle inrush.
Okay, well, thank you. Gosh, that was a lot of information. So I'd like to wrap up by thanking these terrific subject matter experts, Zia Salami and Nicole Kosman, for sharing extensive expertise and knowledge of power systems in industrial buildings. So thank you both. And we do have one more poll for you. A couple of questions will pop up on your screen as soon as this webcast ends. Please take a few seconds to answer these questions. And finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, thank you for joining us, and we'll see you again at the next education session. Goodbye.